Hello and welcome to this video. In this video, we're going to cover the topic of calorimetry, or at least the first part of the topic of calorimetry for students in Alberta taking Chem 30, part of the Thermochemistry unit. So calorimetry is actually something that we use. It's like a lab technique. Just like in Chem 20, one of the lab techniques we did was titrations. Calorimetry is a similar lab technique where it's really useful to help us determine the energy change of a chemical reaction. Okay? A chemical reaction is either going to gain or lose energy, and that energy transfer can be measured by what's happening to the surrounding environment, where the calorimeter is acting as the surrounding environment. So this is an image of a simple calorimeter, or not simple, I guess it could be a little bit more complex, but we have our reaction, again, RXN is short for reaction, taking place inside of this environment, and the reaction is either releasing or absorbing energy from the surroundings. The surroundings here are all what the calorimeter is made of. Okay? Usually the calorimeter is made of water because it's very easy to measure when water goes through a temperature change how much energy it is either absorbing or releasing, measured with our formula Q equals mcΔT. And we know that the energy change that the water is going through is coming from the reaction. So this helps us determine what's happening in a reaction. So what are the steps for using a calorimeter? We're going to want to know, again, the temperature change, usually specifically of water, making up the calorimeter. Sometimes we also have a calorimeter made of an aluminum can or a styrofoam cup, and sometimes we include that in our calculations as well, that we'll look at today. So you're going to want to measure the initial temperature to start anyway, because we need to know the temperature change that our reaction is giving off or absorbing. So you measure the initial temperature of the water in your calorimeter using a standard thermometer. You're then going to add the reactants to the calorimeter. Now this is important. If your reactants are not fully reacting, make sure you measure the initial mass of the reactants. Sometimes it doesn't all react, and you need to know the mass change that your calorimeter is going through, the mass change that your reacting substance is going through. So you're going to measure the initial mass of your reactants. I do a lab with this lesson where we burn candle wax. So we are not burning an entire candle, so we need to measure the initial mass of the candle that's burning. Then again, if this was that candle wax lab, we would light the candle on fire, put the calorimeter over the candle, allow the reaction to proceed, stirring the water to make sure an even temperature is being distributed. If the reaction is exothermic, once you blow out the candle or your reaction goes to completion, you look for the highest temperature that it reaches. If the reaction was endothermic, on the other hand, it's going to make the temperature of the water go down. So then you look at the lowest temperature that it reaches. Either way, you're trying to measure the final temperature of the water so that you can calculate a temperature change. Now at this point, again, if you still have some reactant like a candle left over, you're going to measure the final mass of the reactant. Okay, so when, again, we do this lab with a candle, not all of it burns. So we need to know what mass actually burns, and we find that mass by taking the initial mass and minusing the final mass, because the initial mass is going to be greater than the final. And of course, we obviously want a positive mass change. Okay? Again, delta T will also be found, the temperature change of the water specifically, not the temperature change of the candle. We're not worried about the candle or any reacting substance's temperature change. We're focusing on the temperature change of the water. The water, again, being the calorimeter or the surrounding environment of our reacting system. That's what we're focusing the temperature change on. Okay? This is what a bomb calorimeter looks like. A bomb calorimeter is an industrial calorimeter where you actually put your reacting substances in a little capsule, lower this down, and it's in a completely insulated environment. So all the energy transferred is not, or none of the energy transferred, I guess I should say, is being lost. It's 100% efficient. So we're using our law of thermodynamics that energy is conserved and transferred from the hotter object to the colder object until thermal energy is reached. So what this means is that we are assuming all of the heat lost either by the reaction of the water equals the heat gained. Now it depends again on whether or not the reaction was endothermic or exothermic. Okay, and the way you can tell if the reaction is endo or exothermic is based on looking at what's happening to the water. The water, again, being the surrounding environment, the calorimeter system. Okay, so if the temperature of the water is going down, that means that the reaction is endothermic or absorbing energy. The reaction absorbing energy is what makes the temperature of the water decrease. So this means our reaction is endothermic. And that means when I solve for either delta H or H, depending on what the question asks for, I need a positive value. If, on the other hand, the temperature of the water, again being the surrounding environment, is going up, this means the reaction is releasing energy. And when a reaction releases energy, remember that means it's exothermic. And exothermic reactions for delta H and H always need a negative value. Okay, so I'm always going to start by setting up my reaction with what is losing heat, what is gaining heat. It depends again on whether the reaction is endo or exo as to what's gaining and what's losing. We'll do some examples and you'll see how this unfolds. So for example, let's say I have a bomb calorimeter. Remember again, a bomb calorimeter is just an industrial style calorimeter. It causes the temperature of 500 grams of water to increase. That's a key there. Okay, whenever I'm doing these questions, I always read through the whole question first and see what information we're given. We're looking for the temperature change of the water to know what's happening here. Okay, because again, the temperature change of the water is going up, that means the reaction is exothermic, which means we'll need to put a negative value for our delta H or H, whatever the question is asking for. That also means when I set this up, I'm going to say that the heat is being lost by the reaction. And what is it being gained by? That's the surrounding environment, the calorimeter. More specifically, the water in the calorimeter is what we're going to be measuring. Okay, so heat lost by this exothermic reaction equals the heat gained by the water. Now my reaction side is always going to be measured with a delta H, okay? Because anytime you have a chemical change, you have a change in potential energy, that's measured using the formula for delta H. Anytime you have a temperature change, like what water is going through, a temperature change only, the formula we use for temperature changes is the formula for Q. Delta H and Q both mean energy. They mean the same thing. They just have different formulas. Remember, delta H equals NH and Q equals MC delta T. Okay, this is just how I start my questions, reminding myself that the reaction side, again, is delta H and the water side is Q. Now, if I were solving for molar enthalpy, I would replace delta H with how I solve for it, which is NH. But this question is actually just asking for the heat released by the reaction. So it's just asking for the delta H. So I'm going to leave the delta H as delta H. Okay, because that's what I'm solving for. But Q, how am I going to get Q? I need to rewrite what the formula for Q is to remind me how to find the Q. So in finding the Q, that's going to tell me what the delta H of the reaction is. Now this setup allows me to see that, again, everything that I'm doing on the Q side is for the water. Anything I'm doing on the other side, the delta H side, is of the reaction. Now, what is reacting here doesn't really matter. We're just looking for delta H, okay? So if I'm solving for delta H, I leave it again as it is. So the delta H of my reaction is going to equal the mass of my water, which is 500 grams, times the specific heat capacity of water, which is in your data booklet if you don't remember, 4.19 joules per gram degree Celsius. And my temperature change, again, I always take the bigger temperature minus the smaller temperature. So my temperature change, you could put it all in your calculator in one step, or you can do it in 2 steps. However you prefer is easier for you. If I do it to find the temperature change first, I get a temperature change of 42.0 degrees Celsius. Okay? Remember again, when I'm setting this question up and doing unit analysis, there's no number on the bottom that I'm dividing by. I'm just looking at how my grams cancel and how my degrees Celsius cancel to remind me that I'm getting an answer for delta H in joules. Okay? So in my calculator, I'll go 500 times 4.19 times 42, and that gives me again my enthalpy change in joules. That's an 8. That doesn't really look like an 8. So let's try to make that look a little neater. 87990 joules is my answer. Now this is not finished. Remember, we said that the reaction is exothermic. The reaction is losing energy. So I need to put a negative in front of my enthalpy change. Okay? You're not going to get a negative answer in your calculation. There's different ways of teaching this. I always tell my students at the beginning, remember to write for yourself based on what's happening to the water. If water's temperature is going up, the reaction is exothermic. Therefore, I need to put a negative in front of my answer. Now, I also am being asked to put my answer into kilojoules. So in order to go from joules to kilojoules, you would divide by 1,000. Now, there is a SI prefix chart on your data booklet of page 3, and it tells you that a kilo is equivalent to 10 to the power of 3. So if you have something in joules and you want to put it into the SI prefix of kilojoule, you divide by what a kilojoule is equivalent to, 10 to the power of 3. If you have an answer in joules and you want to if you have an answer in kilojoules and you want to convert it to joules, so you're getting rid of the SI prefix, then you multiply by what the SI prefix represents. Okay? So that's important because you might have things like megajoules, a capital M, in here that you're being asked to solve for. So if you're trying to put it into an SI prefix, you divide. If you're taking it out of an SI prefix, you multiply. Okay? So in this case, I'm essentially dividing by 10 to the 3, which is the same as dividing by 1,000. So if I divide by 1,000, I get an answer of, again, negative, and it looks like I can have 3 sig digs. So it would be negative 88.0, and my units again are now kilojoules. Okay, so if it's asking for the heat released, that is just the delta H. So we solve for delta H by solving for Q, because the Q of the water equals the delta H of the reaction, assuming 100% energy efficiency. So this is the first example of how we solve a calorimetry lesson. Okay, you again have 2 substances. That's how you know it's calorimetry. You have water and something reacting, some type of chemical reaction. Okay, let's look at the next example. The next example is more common to what you're going to see being asked. If I skip to the very end to see what it's asking for, it's asking for the molar heat of nitrogen. Okay, so that means we're not looking for delta H anymore, we're looking for H. Okay, so remember we have our formula, delta H equals NH. This time we're solving for H. Okay, so what that means, again, I'll read the question to find out what's happening to the surrounding environment to figure out if my reaction is endothermic or exothermic. It says that the temperature of the water is dropping. That means the water is absorbing energy. The water is losing energy from the reaction. The reaction is gaining the energy. The reaction is endothermic, which means it needs to be positive. So if the temperature change of the water is going down, that means the reaction is endothermic. So this time when I set up my heat lost and heat gained, this time the heat is being lost by the water, the calorimeter, and it is being gained by my reaction. Now I'm going to say what specifically my reaction is of, because again it just helps me to know, again, when I have multiple numbers taking place here, I know where to use which number. Okay, I'm finding the molar heat of nitrogen. So that's why I'm saying the reaction of nitrogen. Nitrogen again being diatomic. So my water side, like before, is going through a temperature change. Temperature changes always use the formula for Q. And my reaction side is a chemical change. Chemical changes are always delta H. Now you don't have to start there. If you want to go straight to starting with mcΔT equals NH, that's fine. Okay, this is just the stepwise that I go through to help explain it. My water side is going to be found with the Q formula, which is mcΔT, and my reaction side, I'm replacing delta H this time with how I'm going to solve for H, which is N times H. The reason I'm doing that is because I need to see H in my formula, because that's what I'm solving for. Okay? So on this side, again, I'm using the mass, specific heat capacity, and temperature change of the water. And on this side, I'm going to need to find the moles of my nitrogen gas. Okay? Moles, remember, again, can be found with mass over molar mass or C times V, depending on the information the question's giving you. Now in this question, we are being given a mass. So that means we're going to use mass over molar mass to solve for our N. And you can solve for it off to the side and then put it in the formula, or you can combine it into one formula. My N, again, is mass over molar mass, and that's going to be multiplied by my molar enthalpy, which again is what I'm looking for. Okay, so when you do it like this, you see again that there's two masses in this formula, one on the left, one on the right. The one on the left is for the water. The one on the right is for the nitrogen gas. Okay, so if I put those values in, the mass of my water, I'm given a mass in kilograms. I need to always have a mass in chemistry in grams. So to take it out of the prefix of kilo, we multiply by 10 to the 3, which is the same as saying I'm multiplying by 1,000. So I have 1,000 grams. I'm going to multiply that again. This is everything to do with the water. So the specific heat capacity of the water is 4.19 joules per gram degree Celsius. And notice how this question actually gives us the temperature change. It's saying the temperature of the water dropped by 5.82 degrees Celsius. So that is our temperature change. Now, some teachers will tell you if the temperature is dropping to put a negative for your temperature change. I always just use the absolute value. Okay? And then on my other side, my mass over molar mass, again, is of the nitrogen. So the mass of the nitrogen was 8.40 grams, and the molar mass of nitrogen, again remembering nitrogen is diatomic, it's going to be 14.01 times 2, so that's 28.02 grams per mole. And remember again, I like to remove the mole from the bottom and put it on the top. Because when you have a denominator in the denominator of a fraction, it actually becomes part of the numerator. That just makes it easier for me to see how my grams cancel and I'm left with moles. Okay, because whatever you're left with should always be on the top of the fraction. Now that is going to be multiplied by my molar enthalpy, but I'm trying to solve for my molar enthalpy. Okay, so what that means because my moles, mass over molar mass, is being multiplied by H, to solve for it, I need to divide both sides by that mass over molar mass calculation. Okay? So divide both sides. Again, the grams cancel, so this was actually moles. And you can solve for it first and then move it over. It's entirely up to you. I like to do things in one step, so I'm not making any rounding errors intermediately, but it's entirely up to you. Okay? So what this means, when I do the calculation and look at my units, my grams cancel, my degrees Celsius cancel, and I'm left with joules per mole for my units. Okay, so give that calculation a try. Again, this is giving us molar enthalpy. So 1,000 times 4.19 times 5.82 divide by 8.4 divided by 28.02, all in brackets, and you should get an answer of 81344.0, so on. Units again are now joules per mole. Okay, so notice how the question wants our answer again in kilojoules per mole. So I need to divide by 1,000 or divide by 10 to the power of 3, the same thing. And then remember, our reaction is endothermic because the temperature of the surrounding water went down. So that means I need to put a positive in front of my answer. Okay? It's always good to always put a symbol in front of your answer so that you can make sure that you've put a negative when you need to put a negative, right? And technically you should put a positive. So it looks like I can have 3 sig digs. So this would be 81, positive 81.3, and the units again are kilojoules per mole. That is my molar enthalpy for this combustion reaction of nitrogen, the molar enthalpy of nitrogen. And remember before, we could put a little C here, right? Because this is a combustion reaction. Actually, sorry, it's not a combustion. Even though it says it's burning, it's not a hydrocarbon combustion because it's not a hydrocarbon burning. This is actually a formation reaction. This is nitrogen, if we were to write the reaction, which you don't need to do, but this is nitrogen reacting with oxygen to produce N2O. Now this reaction is unbalanced, but it's technically a formation or simple composition reaction. Okay, so that's what the little F would mean if we were to put a symbol there, or if you were to see a symbol there, what it means. But the reaction actually doesn't really affect any of our calculations here. Okay, so that is the most common way you're going to see a question asking you for the molar enthalpy of one of the substances in the reaction. So it's helpful to set it up and solve like this. Okay, we'll look at another example, and that'll be the end of part 1 of calorimetry that we're going to complete in this lesson. So what's different about the next question is that you have a little bit more information. You not only have the amount of water, okay, and the water again has a density of 1 gram per milliliter. So what that means is that if you have 150 milliliters, that means you have 150 grams, okay? Volume in milliliters equals mass in grams for water because of water's density. Now, not only do I have the information of the water, but I also have the mass and material of the can that's holding the water. That's important. If you have a question where you're given a mass and the material is important to help you find the specific heat capacity, you can actually find not only the energy that in this exothermic reaction is gained by the water, but also the can holding the water. Okay? So this is a question where, again, my heat is being lost by a reaction in this case because it says the temperature of the water or the calorimeter, the whole system, is increasing by 7 degrees Celsius. So this means, I'm going to have to erase to make a little bit of room here. This means that the temperature of my water and my can, which is the whole calorimeter system, the temperature is increasing. So that means that the reaction must have been exothermic. So I'm going to need, again, a negative in front of my answer. Now I am looking for the molar enthalpy of ethanol. Look at the units. Kilojoules per mole is molar enthalpy. It also says molar enthalpy, but units of kilojoules per mole means molar enthalpy. And it wants the molar enthalpy. My reacting substance is ethanol. Ethanol is C2H5OH. If you don't remember what ethanol is, or you haven't completed the organic unit yet, in your data booklet on page 4 and 5, there's a list of common molecular compounds like ethanol, and it gives you the formula. So my reaction being exothermic is losing heat, and what is gaining heat now is not only the water, but also the tin can that's holding the water. If you have the mass and material to find the specific heat capacity of the can holding the water, you should always include it. It makes it more accurate, okay? Now, what about the temperature change? What temperature change are we going to use for the tin can? We're going to assume it's the same temperature as the water, the same temperature change as the water. There's some error in that because remember we talked about specific heat capacities. When the specific heat capacities are different, they're going to gain energy at different rates, but we're going to assume it's the same unless the question tells you otherwise. So what that means is on my reaction side, again, my reaction side is always delta H. My water side is always Q, but I'm not only going to have a Q for the water, I'm going to be adding another Q from the tin can. Okay? So if I set this up into my equation, my delta H again is going to be solved with its formula, which is NH. I need to replace delta H with NH because I'm solving for H here. This again is of my ethanol, so I'm going to need to find the moles of my ethanol to rearrange to solve for H. And then I'm going to have an mcΔT calculation for water, and then I'm going to add that to another mcΔT calculation from my tin can. Okay? My N again, because I have a mass of ethanol, the fuel burning in this is a combustion reaction. The fuel burning in this combustion reaction, ethanol, is the fuel. It gives us the mass of that. So again, I'm going to replace N with mass over molar mass, and that will be multiplied by my molar enthalpy. Okay? And again, I'll be doing mcΔT calculation of water and an mcΔT calculation of a tin can. Okay, so in these calculations, there's 3 masses, right? That's why it's really important to set it up like this so you know, again, where you're using which mass. So again, on my left-hand side, this is everything to do with my ethanol. This, on the right-hand side, is of my water. This is of my tin can. Okay, so lots of numbers here. You can do it in individual steps and then add it all together. Totally up to you. Try it however you prefer. I'm going to do it all in one step. So my mass of ethanol is 0.166 grams. My molar mass of ethanol, so ethanol is 2 carbons, which are 12.01. I have 6 hydrogens, 1.01, plus an oxygen, which is 16. So it's 46.08 grams, and remember the mole ends up on the top. And then I'm going to be multiplying that by H, which is actually what I'm going to be solving for. So we're going to have to rearrange that in a second. My grams cancel, and I'll be left with moles in that calculation. Okay, let's actually solve for that. No, I don't want to. Sorry. Okay, no, we will. I keep changing my mind. So 0.166 divided by 46.08. When I do that calculation, I get a number of 0.00360. Now this is why I usually do it in one step, because it's a big long number. I'm not going to write the whole thing down. I'm just going to write a few digits down. Okay, but that is now my moles, and it is multiplied by H, which is what we need to solve for. So if you do it in individual steps where you solve intermediately, you have to remember to use the entire answer in the further calculation when we're going to end up dividing by n to solve for H. Okay? So the mass, now I'm going to go over to my other side and look at the mass, specific heat capacity, and temperature change of my water first. So again, my water was 150 grams, because remember the milliliter volume equals the mass in grams. My specific heat capacity for water is 4.19 joules per gram degree Celsius. And my temperature change, again, I'm given the temperature change. I don't have to find it. Okay? I'm going to be adding that to another calculation, the other mcΔT of the tin can. So that's how this one's a little different. So the mass of the tin can is 25.0 grams. The tin specific heat capacity is in your data booklet on page 3. Tin is 0.227 joules per gram degree Celsius. And my temperature change, again, is the 7 degrees Celsius, the same temperature change as the water. So unit analysis, my grams and degrees Celsius cancel for both calculations. And I'm going to be left with a value in joules that will be added to another value in joules to give me a total value in joules. So let's actually simplify and do that calculation. So 150 times 4.19 times 7 plus 25 times 0.227 times 7 gives us an enthalpy change, or a total Q, of 4439.225 joules. Okay? And now to solve for H, I need to divide both sides by the moles. So the 0.00360, so on, unrounded. Make sure you go up in your calculator and use that exact value, 0.00360, so on, moles. Okay? So I hit divide, I go back up to that exact mole value, and we get an answer of 1232286.057 joules per mole. Notice again, the question wants your answer in kilojoules per mole. So I need to divide by 1,000, and this reaction was exothermic. So I need to put a negative in front of the answer. Okay? So my H, when I divide by 1,000 and put the negative in front, is negative 1232.2, so on, kilojoules per mole. Now when I need to consider my significant digits, everything has 3 digits in it. So I can only have 3 digits, which actually cuts off my decimal. If the number of digits I keep cuts off my decimal, I have to put my answer into scientific notation. That's where we move the digit, the decimal, to after the first digit. Okay, so I'm moving it over 1, 2, 3 places. So what's going to happen for my answer? I'm just going to write it off to the side up here where I have more space. It's going to be negative 1.23 times 10 to the power of 3. The 3 is how many places I move the decimal. And my units, you should always have units with your answer, are kilojoules per mole. So negative 1.23 times 10 to the power of 3 kilojoules per mole. Okay? So that is it for this part 1 of the calorimetry calculations. I'll be doing another video for calorimetry that looks at solution calorimetry, and if you're asked to find for an answer in kilojoules per gram. Thank you for watching this video.